Okay, we're continuing Unit 4, Lesson 7 with some more linear modeling. As soon as you see the word linear modeling, I want y equals mx plus b to pop into your brain. But now, since we're not using points on a line, but we're using a real-world situation, I want you to realize that b, the y-intercept, is now our starting point because every business has to start somewhere. And then our slope is our rate. So when we read these problems, we're always going to look for where did the business start and what rate is it growing, or maybe it's decreasing. Okay. Let's look what we got here. A warehouse is keeping track of its inventory of cardboard boxes. At the beginning of March, they had a supply of 1,275 boxes left. And they use boxes at a rate of 75 per day. Write an equation to model this situation. All right, well, I know I've got to figure out what's my starting point. Well, beginning had 1,275 boxes. So that's my beginning. That's my starting point. Now my slope's got to be my rate. And right here, a rate of 75 per day. All right, but when I go to write this, I'm going to put the 75, and I'm going to use a D for day instead of an X, and the 75 has to be negative because I'm using them up. So I'm minusing 75 every day. And what is that all going to equal? My boxes, which I'm going to represent by B. And boxes depend on how many days have gone by. So there's my fancy equation. So if I were to ask you, what does B of 10 represent? You understand that it means the number of boxes left after 10 days. Okay, if the warehouse needs to order more boxes, when will their supply reach 150? How many days is that going to occur at? Well, now that I have my equation, I'm going to rewrite it over here. All I have to do is figure out, where does 150 belong? I only have two variables here. 150 is either the day, or 150 is how many boxes I have left. And guess what it is? 150 is boxes. So I'm going to put 150 in for here, and then everything else is going to stay the same. Negative 75D plus 1,275. All right, so now I just have to figure this out. I'm going to move this 1,275 over here. So I have to subtract those two. Let's see, that's 5, that's 2, that's 11, and it's going to be negative. I'm going to divide by negative 75. I'm going to be lazy for a minute here. Divide it out. I'm going to find out in 15 days, I'm going to only have 150 boxes left. All right, now for the next one. In 5 days, they start using boxes at a rate of 90 per day. So maybe they've got a big shipment going out. How many days before they run out of boxes? Well, we've got two parts to look at, because for the first 5 days, they're still using their old formula. Boxes depends on the fact that they use 75 a day plus 1,275, what they start at. So if I put 5 in for days, I'm going to figure out how many boxes they have after 5 days. Well, when I multiply that out, that's negative 350, negative 375 plus 1,275. Okay, when I add that together, I get 900. So now I'm going to write a new equation, because the new equation says that after so many days, the boxes will depend on a rate of negative 90 days, negative 90 per day, and on the 6th day, they're only starting with 900 boxes. And I want to know when the boxes are going to equal 0. We're going to have nothing left. So I'm going to set that equation equal to 0, and I'm going to solve it. Move the 900 over to get negative 900 equals negative 90d. And when I divide it out, d equals 10. So again, what's my final answer? If after 5 days they start using more, how many days before they run out of boxes? Well, the answer is 15. Because 5 from the first rate plus 10 from the next rate gives me a total of 15 days. Okay, question 2. The cost C in dollars of running a particular factory that produces widgets. They love to say widgets because widget means like something, anything, little gadget. Can be modeled by this linear function. All right, so now they give us the linear function, so we have to understand what these numbers mean before we move on. Well, 125, since it's talking about dollars, it must mean that it costs $1.25 to make every widget. And then the 2,175, what does that mean? It's probably the startup cost of the business. Okay, so what are they asking us? How do we interpret the fact C of 100 equals 2,300? Well, that means to make 100 widgets, because that's what W stands for, it would cost us $2,300. Better be a pretty good widget. Give a physical interpretation for the two parameters in this equation. So there's a new word, parameters, but that's what we just did to start this off. We wanted to understand this equation before we moved further. We just don't want to look at it and go, CW 1.25W plus 2,000, I have no idea what that means. We want to stop and think about it. We understand linear equations. We understand there has to be a rate and there has to be a starting point. And that's what we said. 125, $1.25 per widget, plus the fact that we had 2,175 startup cost. All right, last question. Look at that lovely, cute deer peering through the thicket. Well, anyway, biologists estimate that the number of deer in Little Rhodey, that's Rhode Island, go Providence Friars, please, let's have a good basketball team this year. In 2003, there was 1,028 of them. Seems a little low. And in 2008, it had grown to 1,488. That's how many I think are in my backyard right now. Anyway, biologists would like to model the deer population P as a function of the years T since 2000. Whoa, wait a minute. This sounds extremely exciting, so let's take our time and figure it out. So I know I have y equals mx plus b. And I know I need a starting point. And I know I need a rate. So how am I going to get all this out of this problem? So first off, we have two coordinate points we can pull out of this. We can say that in 2003, we had 1,208 deer. And in 2008, it went up to 1,488. But there's another really key piece of information in here that we like. Since the year 2000. So we don't need to use 2003, 2008. We can make our life really easy, and we can call this 3, we can call this 8, because 3 years since 2000, 8 years since 2000. That's going to make our numbers a lot easier to deal with. Now, you could have used either one, but again, the smaller the numbers you use, the easier it is to understand. So we would calculate the slope now. That's how we find the rate. Remember, this is the rate. We need a rate in order to write our model, our deer population. So the change in the population over the change in time, because the years will make the deer dependent on how many years have gone by. So I'm going to take 1,488. I'm going to minus 1,028 because that's my population, and the change in time. So the change in time over 5 years, how did this deer population grow? That's 0, that's 6, and that's 4. It grew 460 deer over 5 years. And when I subtract, when I divide that out, 92 over 1, right? So 92 deer per year. And once again, because we live here on Eastern Long Island, that seems really low. But hey, those are the numbers they gave us. Bet you if you look outside right now, I bet you there's a deer in your backyard. Anyway, determine a linear relationship between the deer population, P, and the years since 2000, T. What? Oh, wait, that's now they just actually want us to write the equation of the line. Awesome. Okay, so I'm going to change back to my pretty pink pen. That I have a slope, 92 deer per year, plus, they didn't tell me where I started, because remember, they wanted me to start in the year 2000. They didn't tell me how many deer were in the year 2000. They didn't tell me my starting point. What do I do when I don't know my y-intercept? I have to figure it out. So I'm going to use the shortcut. Where we're going to put in the values for x and y that are on the line, and they have to work. So I'm going to use the first point. I'm going to put in the population of the deer, 1,028. 3 years since 2000. So I'll put 3 in for my t, and that'll figure out my y-intercept. 92 times 3 is 276. Move my 276 over to this side. Let me do some math here. I find B to be 752. So now my equation of my line is the population of the deer is 92 deer per year added on to the original 752 that were around in the year 2000. Let's see what this next question. So how many deer did this model predict were in the year 2000? Hey, we just did that by doing the y-intercept. 752. How many deer does this predict for Rhode Island right now? All right, so I'm going to clean this page up a little bit. And well, this is the year 2015. So the population of the deer is 92 deer per year, and it's been, well, listen to me, I said 2015. Right now it's 2014. I keep thinking it's 2015. I'm putting us up a year. So I'm going to put 14 into there plus 752. Now I use these videos from year to year, so if it's 2015, sorry, I think it's 2014, and if it's 2016, sorry, I think it's 2014, and I'm getting pretty close to retirement, so by the time you get to 2020, I'll be gone. Anyway, put 14 in, because I'm thinking it's the year 2014, multiply it out, and let's see what that little deer population is at right now. So after we figure this all out, we get that there are 2,040 deer in the state of Rhode Island and the Providence Plantations. There you go. It's a little trivia question for you. It's actually the real name of the state of Rhode Island. It's the longest state name out of our 50 states. See ya.